It's nice. Okay. How many people are there? Any idea? Okay. Can you hear me? Hello, dear NPTEL Aqueous Corrosion and its control students. It is a rather very pleasant thing to interact with you live today to discuss about the kind of doubts that you may have on the lectures that were offered so far. And I do hope that these lectures were quite educative in nature. And such live discussion like today probably is very much required for you to clarify whatever doubts that you have in person. So do please let me know what are the questions that you have so that I can address one after another during this 1 hour live session. Can I get the questions? Sandeep, do you have any questions? Can you copy in the chat box? Okay. But are there any people now around? Who are learners now, I think. Okay. Learners, can you guys introduce yourself one after another? Can you please let me know your name and what are you working or what are you studying? They can speak or they cannot speak. Oh, only chat window is it? Okay. So are you guys all happy? You don't have any questions? You should all you make use of this time, very useful time, so that whatever doubts that you had on lectures so far, listen to in YouTube. Right? I do think that you may have some questions. There aren't any questions. Are the TS also there in the meeting? Okay. Okay, and if there are no questions, I'm happy. I mean, that's what it means, right? I mean, those people, at least the four guys who joined, they can listen to me, right? When they're Are they able to listen to me when I speak? Okay. Okay, what do we do in case we don't have any questions? I mean, do we now close the meeting live session? Can you guys? There are four questions. TAs. There are four questions which are unanswered. Can you just tell me what are these questions? Can the TAs put them in the chat box? Okay, then I think can we close it down on the meeting in that case? Yeah. Yeah. Okay. The one question is, can you explain how to apply the mixed potential theory graphically? Okay, that's a question. Okay, let me start uh, explaining this. First of all, I hope you understand what is meant by mixed potential theory, right? Mixed potential theory, excuse me, essentially is applied to a corrosion process wherein you have an anodic reaction, the metals get oxidized, and there could be one or two cathodic reactions. The metals, when they get oxidized, the electrons are released, and in the cathodic reaction, when it occurs, they take away these electrons. So the two reactions are there, at least minimum two reactions are there, one anodic reaction and one cathodic reaction. There can be concurrently additional cathodic reactions as well. So when we talk about the mixed potential theory, what we are looking at is how are these anodic reaction and the cathodic reaction, their kinetic parameters result in the corrosion potential, the corrosion current density. And to do that, the mixed potential theory, we start with the two uh, important points to observe, wherein we say that the corrosion reaction consists of two or more partial reaction. That's what we talked about. There are two or more partial reactions, right? So that's what we said. For example, if I say that iron corrodes in, let's say, in hydrochloric acid, that leads to iron chloride, ferrous chloride, plus hydrogen, for example. Now we consider this corrosion reaction consists of two reactions. One, the iron is getting oxidized as Fe2 plus 2 electrons, and there is also a corresponding cathodic reaction wherein these electrons are accepted to liberate hydrogen like that. In the process, there is also second condition where this is the rate of oxidation. This is oxidation of this, right? And this is a reduction reaction. Right? So the mixed potential theory says the rate of reaction 1 reaction 1 is equal to the rate of reaction 2. So this is what the mixed potential theory says. Why does the theory say that the rate of reaction 1 must be equal to the rate of reaction 2? Because the charges released and charges accepted must be the same. The metal will be always neutral. The metal cannot be either positive or negative. If it is, for example, positive, then what happens? This reaction gets slowed, and automatically this reaction gets slowed actually. So this is the mixed potential theory which talks about. This actually is nothing but law of conservation of mass we talk about actually. Now when I talk about mixed potential theory, then we need to start with two important points of how do you define the rate of reaction. The rate of reaction is related to what? Is related to the current density that we talk about. Now the current density, okay, we talk about is related to the over potential, right? What is over potentials? Over potential is equal to E equilibrium, okay, plus over potential is equal to E applied. This all I think we would have studied or listened to my lectures. So there is a relation between this over potential that we talk about and the current, which is related to rate of reaction. That is given by the two reaction eta is equal to eta A anodic reaction is equal to, okay, plus beta log I upon I naught external current density. And similarly, we also have eta cathodic reaction is equal to minus beta log I upon I naught. Okay. So these are the two equations which are all fundamentally that we know about it, right? These are the things that we know about it. These are called as the Tafel equations. Okay. Now let me, because I am going to define the mixed potential theory in slightly different manner because you guys might have read these things now. Let me use this to define the mixed potential theory and see what it means actually. Okay. Okay. Let me look at the mixed potential theory wherein, let's say, you have potential axis and the current axis. The current axis is given as log I, and the potential axis is given here. Okay, A is potential. Okay, and it is going to be toward this side is positive, and this side is going to be negative here. Now there are going to be two equilibria to start with, right? For example, you may have Fe2 plus 2 electron gives you Fe. There's one equilibrium that we talk about. There is also another equilibrium that we have, which is 2H plus let's say 2 electron gives you hydrogen gas. These are the two equilibria that we talk about. Each of them will have its own equilibrium potentials. Now this can be now represented in this diagram, okay? That is, it's called also called as events diagram. That is what? That is potential versus the current flow. When these are all under equilibrium condition, there is no oxidation, no reduction takes place. Now you represent this in this diagram. Let's say I am representing this, the equilibrium potential of this, some equilibrium potential somewhere coming here. Okay, this is the equilibrium potential of our ion. Okay, if I am going to take this as standard state, I think probably its value is going to 0.44 volts, for example. This is standard state. I take this as 0 volt actually, right? Is the equilibrium potential for this and this, and then the corresponding exchange current density is also can be placed in the same graph. So I represent this equilibrium in this graph in this particular point that corresponds to equilibrium potentials, that corresponds to what? The exchange current density here. And this equilibrium corresponds to the ion Fe2 plus 2 electron is equilibrium with ion here. And I also represent what is called as this H plus electron here, which is again is relatively positive, that comes somewhere here. So there is a equilibrium potential and there is an exchange current density here. So I'm going to represent two equilibrium here, right? Now, when I represent this two equilibrium, let me look at the corrosion process. What is the corrosion process? I've taken an acid in a beaker, for example, right? Now I'm going to immerse this, this ion sample in, let's say in hydrochloric acid. Okay. Now the reaction that takes place are a hydrogen evolution and then ion oxidation takes place. Okay. Now what is happening now in this case is that, okay, now let me see now what happens. Ultimately, these two equilibria, they get disturbed and the corrosion takes place wherein hydrogen starts evolving here, right? And ion is getting oxidized as Fe2 plus here. And of course, there is electrons get released and they travel here, and H plus from here come and accept it, okay, and becomes hydrogen. Now it is going to attain one potential wherein the rate of hydrogen evolution is equal to rate of ion oxidation. That's what we saw before. So that is going to be a potential in which the metal will exist, and that is called as a corrosion potential. Now, how does this happen? That's the question now. Okay, how does it happen? Can we define this using the Evans diagram, using the mixed potential theory? Now we start with what is called as equilibrium, right? That is, when the moment I immerse metal here, let's say ion exhibits a potential somewhere here, right? And there is one equilibrium of ion here, there is equilibrium of hydrogen here, right? There are two equilibrium that happens, okay, just in the moment of it, that is represented by this exchange current density as well as potential here, and so as this also. There are two different potentials. At the time t equal to 0, these two equilibria exist now. But because the metal is getting shorted, electrically there is no resistance at all. This potential that we exhibit here for hydrogen, this is for hydrogen, right? This is for hydrogen, right? H plus is in equilibrium with hydrogen here, and this is what happens. This ion is in equilibrium with Fe2 plus, right? These are what it is going to be. They are in equilibrium conditions, okay? Momentarily, they will exhibit a potential is equal to this, and this equal to this here. Because the metal is conducting, the potential will not remain the same. So that means the potential will start moving up, this one start moving up, and this guy starts moving down, right? Now, when the potential starts moving down, what happens now? That means what happens now, what will happen to this equilibrium? This equilibrium will start moving towards because when we are moving down here like this, it is moving towards negative direction. The equilibrium will now becomes what? Plus H plus electron gives you hydrogen. What happened to this equilibrium? This equilibrium will go into Fe, going as Fe2 plus 2 electron here. So this is going to happen. So that means what is it? When I go to move the potential, how the current will change? The current will start moving like this. And what is the relation between this? This is your equilibrium potentials. Any deviation from here to this is what? This is called as a over voltage. Okay, and though, so this particular relationship that you talk about will follow the relation is equal to eta is equal to minus beta taper slope beta c log I upon I naught. What is I naught? This I naught corresponds to this, right? And I corresponds to any eta value that you talk about, any eta value that you talk about corresponds to this I here. And this slope corresponds to this value here. So that means this particular relationship that is following here is essentially following the so-called Tafer relationship. Similarly, what will happen is this guy also will start moving down. That means it is going to follow a relationship which is equal to this actually here, right? And this guy will follow a relationship eta is equal to, is equal to plus. Until I made a mistake, please correct it. This corresponds to beta positive because this anodic reaction goes like this, and this eta which is equal to minus beta. Again, this is anodic reaction. Please correct it. Pardon me for the mistake. Okay, eta is equal to minus beta log I upon I naught. Okay, so look at this follows this line here, and this follows this line. Okay, that's what really happens, right? So they are following this line essentially. Okay. Okay. Now, when it happens, okay, let me go back to this. Okay, when it happens, okay, it is intersecting this particular location. Look at this. This is a place where this line is intersecting. This line is intersecting at this particular point. The rate of oxidation is equal to rate of reduction because the current is going to be the same. So the mixed potential theory says that the rate of oxidation is equal to rate of reduction, and so this is the point that metal will start exhibiting here. At this point, this is the potential that corresponds to what? This corresponds to E car, and this is potential that corresponds to I car here. Okay, so the mixed potential theory basically means that you are able to visualize corrosion process as at least two reactions. One is an oxidation reaction, other is a cathodic, other is a reduction reaction. The oxidation reaction has its own kinetics. The reduction reaction has its own kinetics. But however, what is common for both of them is when both the reactions occur on the metal surface, the rate of oxidation is equal to reduction. That means both the reactions are pinned and you get E car here and you get I car here. Okay, this is what I mean by the mixed potential theory. I hope you people understood what is meant by the mixed potential theory actually. Okay, so okay, so what is happening in this video at this thing? I am not understanding what it is. I have a question about what is happening in this video at 002.27.05, and I don't understand. Can you explain what it is actually? It's hard for someone to remember what has been recorded at 27 minutes and 5 seconds. Can you yeah, so I failed to understand why the intersection of the red line with the black line was considered to be the point where rate of oxidation equal to rate of reduction. I do not understand what this question is in relation to the lecture actually. Can you elaborate on this actually? What is the background context in which this has been talked?
Hello.
Yes.
Yes, sir. Abhijit here.
Yes, Abhijit.
Yeah, sir. The question it was related to what you explained right now. There was a question how exactly the rate of oxidation becomes equal to the rate of reduction, and that is what you explained. So I think what you explained it covered the question. So exactly how to apply the mixed potential theory in graphical format, that was the question from the learner. So I guess you have covered it.
Okay, so thank you so much. Okay.
Thank you, sir.
Oh, can you take, sir, some examples of small multiphysics corrosion module? Okay, of course, it's a good question, but I don't think I have handled COMSOL multiphysics corrosion module. I think, COMSOL corrosion module would have a different type and various type of problem solvings, right from cathodic protection. I mean, yeah, cathodic protection, galvanic corrosion, solving the problems and all. And I don't think I'm familiar with the multiphysics corrosion module, but I think that should not be a problem. We should start learning that thing as you um, start working on the COMSOL multiphysics corrosion module. And of course, you can also take the help from the COMSOL people in terms of how do you really handle this particular program. Yeah. Any more questions? Okay. So if there aren't any questions, can you move on? Can we? Okay. So thank you so much, the learners, and I wish that you people come out with more questions, because that only implies that you people really going through these videos more seriously. Okay. So thank you
Hello.
so much, and please do correspond, and we do interact even offline. If there are questions are there, I think we should shoot the questions. TS are available. I can also help you in understanding the concepts. No problem at all. Okay, so there is no further questions. Maybe we can close it, okay? And we encourage the people to come prepare with more questions in the next session. Okay. Yeah. Thank you so much. Thanks, Abhijit.
Yes. Thank you,
Thanks,
sir.
Sugni.
Thank you,
Thank you.
sir.
Yeah. Okay. Fine.